Okay, so we're already beginning to learn how to work with occupation number states. To go further, I want to introduce an operator. So I want to introduce the operator capital N. I use capitals for the operators, N of K. And when this acts on my occupation number state, ket N, this is going to give me little n of K, which means the number of particles of momentum K. So N of K is the number operator, and it counts the number of particles of momentum K. The momentum operator acting on the occupation number ket can be written in terms of N. So it's given by, I've got a sum over all of the discrete momenta. I have got the number of particles of momentum K multiplied by K, and this is all summed. So if I now allow operator N of K to act on the state N, so the only thing here is the operator N of K, K is just a number, I would get a sum over K, replacing the operator by its eigenvalue. I am simply counting how many particles there are of each momentum and then adding that up. So that's the formula for the momentum operator acting on the occupation number ket. And there's also a very simple formula for the Hamiltonian. And I bet you could guess it, but let's write it down. So the Hamiltonian on the occupation number ket, you still have a sum over K. We're going to work out how many particles there are of momentum K and multiply it by the energy of a particle with momentum K. And then this then gives you, again, the very intuitive formula that I've written at the bottom of the page. Good. So that is a formula for the momentum operator and the Hamiltonian acting on the occupation number ket. So this is much nicer than the wave functions that we were studying when we first thought about Fock space. But we can do even better. In fact, it's possible to drop wave functions altogether. And we are going to do that. In the end, we will not work with wave functions. We will just work with the fields themselves. But there are situations where people insist on using wave functions. For example, in many body physics and condensed matter physics, often that's the case. And in that situation, you should always work with the occupation number representation because that's the simplest possible representation to use. And now I want to point out what looks like a formal analogy, and we're going to explore it a little bit because we'll see there's actually a lot of depth here. There's a lot of things to understand. And my observation is that things look a lot like the harmonic oscillator. So let me explain to you what I mean. So you've studied the harmonic oscillator in your non-relativistic quantum mechanics course, and you might remember that after a little bit of manipulating things and introducing signals and dropping a ground state energy, your Hamiltonian looked like omega times by A dagger A. A dagger A was the number operator. It simply told you how many quanta there were inside your state. So you often denoted that as an n hat for the number operator. So we've got the number operator multiplied by the energy of one quantum. Wow. This looks a heck of a lot like the formula that we've got, where we've got omega k, we've got the number operator. So the two formulas look very, very much alike, and that is not an accident at all. The system we are studying, so we are studying a collection of harmonic oscillators. So we're studying a collection of harmonic oscillators. Actually, it is an infinite collection of harmonic oscillators. Each is labeled by K. So you should think about the momentum K as a label for harmonic oscillator. There's an infinite number of values of K, so there's an infinite number of oscillators in our collection. And this collection of oscillators is what we mean when we say that we're doing quantum field theory. Quantum field theory is the dynamics of an infinite collection of oscillators. We're going to return to this idea a few times to make sure that it's completely clear. But the idea that you should have in your head is that quantum field theory is that theory that results from studying an infinite collection of harmonic oscillators. If it's a free quantum field theory, then the oscillators are not coupled to each other. But when you introduce interactions into the quantum field theory, these different oscillators do interact with each other. And we'll see both examples as the course proceeds. One question that you may be asking yourself, when I tell you you studied the harmonic oscillator in quantum mechanics, and I said to you, well, what got quantized? You'll tell me energy is quantized in the quantum mechanical description of the harmonic oscillator. Now here, we could ask, what is quantized in quantum field theory? So what are we breaking up and making discrete? Actually, the field itself, the field is quantized. The field, so remember in the harmonic oscillator, the energy didn't vary continuously. You could have an energy of omega or 2 omega, but nothing in between. So there was one energy level, a gap, and then another energy level. So energy didn't vary continuously. There was a discrete set of values that energy could take. Well, here, the field varies discretely, not continuously. So the field itself varies discretely. You have packets of field, or maybe say bits of field, a little bit of the field. And it's, this little bit is the smallest bit you can get. You can't slice it up further. Well, these bits of the field, these packets of the field, we usually call particles. So the electromagnetic field is made up of bits, and each bit of the electromagnetic field we would call the photon. In fact, every field in nature is quantized, and the quantum of all of those fields corresponds to a particle. So there are electrons, these are particles, but electrons are the little bits of an electron field. There are positrons. The positrons are a little bit of a positron field. Quarks. Quarks are little bits of a quark field. So in quantum field theory, it's the field itself that gets quantized. Things look a lot like harmonic oscillators, but the quanta of the field, it's not that you've added a bit more energy to your state, it's that you've added another particle to your system. What I want to do next, I want to give you a little bit more insight into why it is that the harmonic oscillator plays such an important role in quantum field theory.